This dual-polarization weather radar works because pulses transmit in two orthogonal dimensions. The clever bit here is wave orientation. Conventional single-polarization weather radar transmitted only horizontally aligned electromagnetic pulses into atmospheric clouds. It measured returned signal strength, but could not determine particle shape or geometry. Transmitting radio energy across two axes allows radar to analyze target cross-sections directly. When radar engineers first attempted to evaluate severe weather intensity, they assumed that total reflected microwave energy directly correlated with overall rainfall volume and cloud precipitation rates. However, relying purely on single orientation pulse transmissions presented a fundamental physical limitation when encountering diverse atmospheric precipitation targets with varying structural cross-sections. A single horizontal radio pulse hitting a large flattened raindrop reflects back roughly the same signal power as when striking a compact spherical hailstone of equal mass. Because early single-axis weather radars only measured raw return signal power, forecasters could not distinguish spherical hail particles from extremely heavy liquid downpours inside storms. A massive hail core and a dense curtain of small liquid water droplets produced confusingly identical high reflectivity echo intensity patterns on standard operational radar screens. Relying solely on total echo power created dangerous atmospheric classification errors, masking critical aviation hazards and producing wildly inaccurate localized flood risk calculations. To overcome this single-axis ambiguity, modern weather radar systems were re-engineered to transmit paired electromagnetic pulses along both horizontal and vertical polarization planes simultaneously. By continuously measuring and comparing the returned microwave power along both axes, the radar receiver calculates fundamental geometric and structural properties of every atmospheric target. As raindrops fall through atmospheric air resistance, aerodynamic drag flattens them into distinct oblate spheroids and are significantly wider horizontally than they are vertically. The horizontal radio wave encounters a broader physical cross-section, reflecting noticeably more electromagnetic energy back to the dish than the narrower vertical wave encounters. Comparing returned horizontal power directly against vertical return power calculates differential reflectivity, establishing the average geometric axis ratio of precipitation particles within the volume. This dual-pulse comparison instantly distinguishes oblate flattened raindrops from perfectly spherical hailstones that reflect both horizontal and vertical wave axes with equal intensity. The bigger problem was that real thunderstorm clouds contain billions of mixed particles tumbling at high velocities inside chaotic turbulent updrafts.
Inside violent convective storms, melting ice crystals, giant raindrops, heavy hail spheres, and non-weather debris mix together across a single volumetric radar sampling cell. A basic ratio of returned horizontal and vertical energy becomes severely scrambled when thousands of irregularly shaped, tumbling targets scatter microwave energy in all directions simultaneously. Furthermore, as electromagnetic wave pulses travel through dense curtain walls of heavy rainfall, energy along the horizontal axis attenuates much faster than vertical wave energy. It appeared nearly impossible to determine whether returned power differences reflected genuine target geometry or progressive differential wave attenuation occurring along the transmission path. Randomly tumbling hailstones and biological clutter created intense signal noise, making simple intensity ratios far too unreliable for automated hazard classification inside severe weather systems. To accurately identify particle shapes hidden deep inside severe storms, engineers needed parameters beyond power ratios, incorporating precise electromagnetic phase timing and pulse alignment. The complete dual-polarization engineering methodology calculates three distinct mathematical parameters for every volumetric sampling cell grid across the radar scanning range. First, differential reflectivity isolates target physical shape by computing the direct logarithmic ratio between returned horizontal power and returned vertical power measured in decibels. A strongly positive differential reflectivity value signals broad oblate targets like giant liquid raindrops, whereas near zero values reliably indicate tumbling spherical hail particles. Second, the radar receiver measures differential phase shift, tracking subtle travel time delays between horizontal and vertical radio waves as they propagate through cloud precipitation. Because horizontal waves encounter wider liquid water surfaces, they suffer greater propagation delay, travelling slightly slower than vertical waves through heavy precipitation zones. This phase delay accumulates steadily along the beam propagation path, providing a robust measurement of total liquid water content completely unaffected by microwave signal attenuation. Third,
The signal processor calculates the correlation coefficient, measuring how consistently horizontal and vertical pulse returns fluctuate together over consecutive radar pulse trains. Uniform weather targets, such as pure raindrops, produce extremely high correlation values, near 1, demonstrating identical scattering behavior between both polarization channels. Irregular targets, like tornadic ground debris, birds, or flying insect, scatter horizontal and vertical waves unpredictably, causing correlation coefficient values to drop precipitously.
By cross-referencing differential reflectivity, differential phase shift, and correlation coefficients, automated algorithms instantly classify hydrometeor types across every layer of a storm. Radar operational software utilizes these combined parameters to detect tornadic debris signatures, providing immediate confirmation of active ground damage inside severe storm cells. The system simultaneously segregates heavy rain bands from hail cores, enabling precise real-time flash flood warnings and accurate hail size estimates across regional networks. Advanced real-time signal processing corrects for path attenuation using phase shift data, restoring true reflectivity values even through dense, severe squall lines. Treat radar interpretation as an explanation of instrumentation, not as a substitute for official forecasts or warnings issued by responsible meteorological authority. Do not encourage approaching radar transmitters or entering restricted radar sites under any circumstances when inspecting operational weather radar equipment. By continuously transmitting orthogonal horizontal and vertical pulses, dual-polarization radar transforms simple echo reflections into explicit structural particle measurements. Comparing subtle differences in returned wave power, accumulated phase delay, and signal coronation reveals the exact physical target shapes hidden inside storm clouds. Engineers successfully transformed simple radio echo timing into a high-precision volumetric diagnostic instrument for monitoring complex severe weather atmospheric physics. Dual-polarization radar illuminates the hidden internal structure of severe storm systems, converting raw radio scattering into actionable, life-saving physical intelligence.